Now you can hear me, right?
Yeah.
Okay. Yeah, so thank you very much for having me today. As you already introduced me perfectly right, I want to talk a little bit about pH-influenced active motion today. The data I'm going to present is from this publication, which we got out this year in spring. And if you are interested, of course, you can always find more information there. I want to start my talk at the point that we probably all know. I want to talk about the state-of-the-art photocatalytic microswimmer. If you think about such kind of microswimmer, of course, probably you will think about a Janus particle that looks somewhat like the one I am showing you here. It is based off some photocatalytic material, usually like titanium dioxide, that when you excite it with light, will create excited electron-hole pairs. And then usually you coat it with a co-catalyst like gold, where the electrons are transferred to. So you have charge carrier separation. Different half reactions will go on the different particle sides. For example, here, when you use hydrogen peroxide as a fuel, and then eventually you get active motion. What you probably also can imagine is that for this kind of microswimmer, you have to go through multiple steps to actually get it, and the yield is somewhat limited. If you imagine how you would make it, there would be more or less 3 steps. Of course, first you would somehow need your base particle, which could be titanium dioxide microparticles. You would probably synthesize them. And then if you are happy, if they are fairly monodispersed, then you would somehow passivate one hemisphere of the particles to later, in the 3rd step, coat the other hemisphere to get a Janus particle after all. And this passivation step is very crucial. For one, the monolayer you make there, for example, by Langmuir-Blodgett methods, needs to be very even. And on the other hand, it cannot be infinitely large. So you are always limited with the yield of your swimmers by how many microswimmers you can somehow deposit at once and coat at once. Naturally, your batches of swimmers will differ, and this, of course, reduces reproducibility, which is nothing we want. So at this point, we thought maybe we can make swimmers that are actually a bit different. What if the next generation of microswimmers could be like this? You just synthesize them, you do just one single step, and then they can already move actively. You already have a working microswimmer. No passivation, no deposition, no nothing. Now you probably wonder, okay, this would be cool, but how could this swimmer look like? And this is also something we thought about. And after a while, we thought, okay, maybe we just need to move away from the everlasting titanium dioxide that we use all the time. And the material we decided to go for was bismuth vanadate. That's a mixed metal oxide, also a photocatalyst, so you can also excite it and create electrons and holes. The particles you can synthesize, when they are single crystals, they look like this. They have this truncated bipyramid as a shape. And the fancy thing about them is they can separate electrons and holes without the need of a co-catalyst. This works by a concept that is called surface heterojunctions. If you look at the right of this scheme here, there you have the energy levels of the 2 facets, which are exposed in single crystalline bismuth vanadate. It's the 010 facet and the 110 facet. And what you can see in this scheme is that the energy levels are a bit different, although of course the band gap is the same. So basically, you have a type 2 heterojunction here, and when you excite with light and create electrons and holes, then electrons will migrate to the 010 facet and holes to the 110 facet on the surface of this particle, which you can also see here in the scheme. Holes will go to the sides of the particle and electrons to the top and the bottom, because this is just where the facets are. And this would mean then that you can have spatially separated reactions and a gradient and active motion without the need of making a Janus particle or putting a second catalyst on this, and that you could just synthesize it and they start moving. This sounds already really cool. The only thing that was a little bit stopping us was, if you look again at this SEM image here, you will see that the particles are rather far from being monodispersed. You have a very large particle here, which is about 5 micrometers in size, but then also a rather small one, which is maybe only 2 micrometers and much thinner. And of course, this wouldn't work if we want to have a batch of microswimmers that all behave the same. So I changed the synthesis a little bit and tried some things. And eventually I came up with this synthesis protocol here, where I get polycrystalline bismuth vanadate microparticles. So still the same material, just they are not a single crystal anymore, but assembled out of many small crystallites. By changing the pH in the synthesis from 2 to 3, I can also change the particle shape. You can see here in the SEM images, at pH 2, we get these rather spheroidal particles, and at pH 3, we get these ones that we call stacked or sometimes also square-shaped particles. Now you probably wonder if we still have this fancy surface heterojunction here and electron hole separation. On the spheroidal particles, at this point we assume the crystal is not very oriented there, so electrons and holes should be distributed randomly under excitation. However, at the stacked particles, you can probably already guess from the SEM images, they are most likely stacks of these single crystallites that you saw before along the electron-rich facet, which means that we can still accumulate holes on the side, as you can see in this sketch here, and electrons on the top and bottom. So we still have electron and hole separation. Now the prize question is, do these particles actually move? And for this, I brought you some videos. First, for the stacked particles, they are usually immersed in peroxide under UV illumination, and you can see when the UV light is shining on them, they rotate by 90 degrees, they kind of stand up, and then they start moving actively, although they only consist of one material. So there must be sufficient asymmetry for them to actually move. For the ellipsoid or spheroidal particles, the conditions are similar, again peroxide and UV light, and again you can probably see that they move actively and don't only do Brownian motion, although they are a bit slower, and they also don't do anything like this standing up, which we just saw for the stacked particles. This may just be because the crystal is less oriented here and the particles are therefore a bit less active. Nevertheless, at this point we can say active motion is definitely possible with microswimmers that consist of only one material and that were produced in only one step. If you care to read a bit more about these specific morphologies, I could recommend you this publication about the stacked particles, which we published 2 years ago, and about the spheroidal particles. We found something else interesting. We found that they can actually assemble into modular microswimmers from 2 to 4 building blocks, and then they move together. And the motion mode also depends on how many particles are there in one assembly and how are they assembled, in which geometry. This we also published together with Benno Liebchen last year in Langmuir, and yeah, you're also happy to look into this one. But now I promised you something about the influence of pH on active motion, so now let's actually get to pH, and from now on I will talk about the more active stacked particles. What you can see here in this scheme is on the x-axis different pH values, and on the y-axis the speed of the particles at this pH. So we always have the particles on a plain glass substrate in a diluted peroxide solution, and then we change the pH to acidic or to alkaline to monitor the speed of the particles. What you can probably see on first sight is that the speed is usually more or less the same from acidic to neutral pH, but then something really interesting happens at pH 10. The particles get much, much faster and then they slow down again. I can illustrate this for you also here. The only difference between the two videos is the pH. You can, and you can see at pH 10, the particles are much faster. Now, the question is a little bit, why does this happen? How does the pH change make the particles faster? And for this, we need to look a bit more into the environmental conditions of the solution the particles are in. I brought you two more plots to solve this mystery. One contains conductivity of the solution and the zeta potential of the particles. The other one, the rate constant of peroxide decomposition by our catalytic particles. If we look at the middle plot at first, then we can see the zeta potential, which is the black markers in this plot. We can see it is positive for pH values below 3.4, that's this dashed line here. And then it gets negative for all other higher pH values. So this means the particles are neutrally charged at 3.4, positive below this pH, negative above. But this clearly doesn't have anything to do with our speed change because nothing really happens around this point of zero charge. The conductivity, however, is of course naturally quite high for extreme pH values because we have a lot of ions there. That's the blue markers here. It is high in the acidic regime and high in the very alkaline regime and lower for everything in between. Now, as we know, very high conductivities usually slow catalytic microswimmers down. That they are slow again here at the very extreme pH is maybe because the conductivity gets very high. But that they get fast at pH 10, that is to be found here in the peroxide decomposition. You can see the rate constants or the kinetics of the reaction is more or less in the same order of magnitude for everything that is acidic and for neutral conditions up to pH 8, where the reaction starts getting faster. The rate constant increases. This just means the catalytic activity of the particles increases. And of course, if they are more active, they also will move faster. So what we observe here on the top in this speed scheme is that the particles speed up when we get to the alkaline regime because there is such a high activity, but then they also slow down again because the ion concentration gets too high and this slows them down. So we found by changing the pH, we can change very easily the maximum velocity of our swimmers. Something else, even more fascinating, we can change with pH is the motion mode of the microswimmers. So here again, you have the plot of the speed that you already know, but below now you see a plot of the motion mode, which just means the way the particles move. You already saw that for neutral conditions where we watched a video before, the particles rotate by 90 degrees and then they move when we illuminate them. This is what we call upright motion. And this is what happens at every pH above this point of zero charge. And this is the black bars here. If we go below the point of zero charge, so if we make the particles positively charged, then you can see they perform a different kind of motion that we call horizontal, which essentially means they don't do this upright motion anymore. I can illustrate this. So here we have neutral and alkaline solutions, and you see as soon as light is shining, the particles stand up and move. So this is upright motion. But now, if we go to solutions between pH between 2 and 3, there the particles are positively charged. And there you can see that when the light is shining, they move actively, but they don't stand up anymore, which is what we call horizontal motion. So it pretty much seems up to this point that we can use the pH for our photocatalytic microswimmers to change their speed and to also change their motion mode. And at this point, we thought, wouldn't it be really cool if we could control this behavior? Wouldn't it be interesting if we could have a substrate where in one area the pH would be higher than 3.4, so our particles are negatively charged and they move upright, like this one particle here. But then if it moves to a second area where for some reason the conditions are different and the pH is lower than 3.4, it becomes positively charged and it moves in a horizontal kind of way. This would be interesting because at the moment we cannot have this flexible change of motion. At the moment we just make a pH of our solution, of our droplet, and then we observe it. But of course it would be much more interesting if we could control and switch the behavior. Now you may wonder, how could you do this? And the answer we found are excited state photoacids. Maybe you have heard about this kind of chromophore. It's just an organic fluorescent molecule that has an acidic proton. So basically the general formula could be ROH. Then of course this molecule can dissociate with an acid constant K1, create an anion and a proton. The special thing now about the photoacid is you can also irradiate it with light, then it becomes excited, which I marked with this little star here, and then it can also again dissociate with a new acid constant K2. And the special thing is that K2 is by orders of magnitude higher than K1. So in general, this means if you have a solution of this dye, then if you shine light, the solution pH will drop a lot. But if you don't shine light, nothing much will happen. So we thought, is this maybe the answer to what we want to do? Could we maybe coat our substrate in a distinct area with this photoacid? Then we shine light anyway to propel our microswimmers. And then would the pH drop in this area where the photoacid is immobilized? So we found collaborators which were happy to do this with us from the group of Gregor Jung at Saarland University, who provided this photoacid to us. You can see it's a pyranine derivative with the acidic proton here in the top left. And when you shine UV light on it, it goes to this excited state and transfers a proton. This behavior you can also see in spectroscopy of this dye. So here you have absorption and emission spectra of the dye in solution at different pH values. What you can see is in the absorption spectra, you have peaks of two species. If the pH is very high, so you have a very alkaline solution, then you only see absorption features of the deprotonized form of the dye. But now if you add protons, if you make it very acidic, then of course you will protonize this deprotonized form, and eventually you only see absorption of the protonized form, the more acidic you go. In the emission spectrum, however, it is different. You see there's only one peak here, only the peak of the deprotonized form. And that's because it doesn't matter at which pH you are, which species is present. As soon as you shine light to excite it, it will do excited state proton transfer, and you only ever see the emission of the deprotonized form. So this is exactly the proof that we have this excited state photoacid here. Now, we somehow had to immobilize this to our substrates. So at first we thought, let's just immobilize it on particles, which is what you can see here. So we can see how does it behave when it's immobilized, but still we can do spectroscopy rather easily. So we coupled it to Aptis, which then nicely binds to silica nanoparticles. And you can see again absorption and emission spectra that look very similar to what you just saw and that show us we can still do excited state proton transfer also if the dye is immobilized. So the next step was to coat it to our substrates. We did the same protocol there, again first coupled to Aptis, and then coupled to glass substrates and not nanoparticles anymore. The results I will show you now. So the data you see now is fluorescence imaging of these coated substrates. In the plot here on the left, you have on the x-axis different dye concentrations during functionalization. On the y-axis, the mean gray value of the substrates later when we did fluorescence microscopy. So you can take this as an indicator for the brightness of the substrates later. Naturally, what you can see is if there's more dye in the functionalization, of course, the substrates later will have a higher mean gray value, which just means there's more dye and they are brighter. So this is something you would expect. What was a bit unexpected to us is what you can see here in these microscopy images. You can see that there are areas where there's a lot of dye and it is very bright. But then there are also areas where there's not so much dye and the area is darker. So basically you have islands where a lot of silane probably agglomerated, and then areas where this is not the case. And this is of course something we need to know if we now want to see how the swimmers actually move on these substrates. I brought this data for you here on this slide. Maybe first, what do you see here? On the x-axis, again, you have the concentration of the dye during functionalization. So left is very little dye, right is a lot of dye. And on the y-axis now, you see the fraction of each motion mode that we observed on these substrates. So in theory, what we did here, or not in theory, also in practice, we took the substrates, which are coated with dye, and then we added a neutral solution of particles and peroxide to the substrate, illuminated with light, and observed the motion of the particles. Now, we assumed that if we have more dye on the substrate, this would then decrease the pH when we illuminate it, and then make the particles move horizontally. For comparison, again, I have the motion mode plot you saw before here, where we didn't have any functionalized substrates, just plain glass. And also there, when we added neutral solution of particles and peroxide, then this condition here at pH 6 would be the one you have to consider. So basically everything we are comparing here on the left side, we are comparing to this condition. As you can immediately see, there's definitely a difference. Normally, we don't have any motion in horizontal mode on our neutral glass slides, but on the functionalized one, we have horizontal motion for each dye concentration. What you can also see is that there's now a new motion mode, the red one that we call tumbling. I can show you what tumbling means. It is motion of particles which cannot really decide if they are going to move upright. Like now you see they are trying to stand up, but then also they lay down again. And so over the course of the video, you cannot really decide what kind of motion you see here. Overall, if we interpret this plot, I think we can say that yes, there is an influence of the functionalized substrates on the swimmer motion, but unfortunately, this influence does not increase with increasing dye concentration during functionalization. I also have a comparison here for you where you can see on the left, there's a plain glass, On the left, you got a plain glass substrate where no dye is present, all the particles move upright. On the right, there is the substrate functionalized, and you see the particles move in a different way. So definitely the dye has an influence on the particle motion, probably by decreasing the pH of the solution. At this point, I'm at the end of my talk. I have shown you that we can make single component microswimmers that are inherently asymmetric and that just start to move after the synthesis. These microswimmers, which consist of bismuth vanadate, move happily at a very broad pH range, and by changing the pH to the more alkaline, we can make them move faster. By making the pH more acidic, we can change their way of motion. And eventually I showed you that this pH change can also be achieved from the substrate by coating the substrate with a photoacid. This work was mainly done by my bachelor student Julia Hübner last year, who of course I would like to thank at this point, as well as our whole group and the group of Gregor Jung at Saarland University, who provided the photoacid to us, Professor Wang for inviting me today, and of course you for your attention. Thank you very much.
Thank you, Sandra. Thank you for your wonderful talk. And now we are going to the Q&A session. If you have a question, just unmute yourself or put this question into the chat box.
May I ask a question?
Yeah, sure.
Thanks for your talk. In your presentation, when pH is neutral, the particle will assemble. So what is that? Does it still assemble when the pH is low, which is below the 3.4? I mean, their moving behavior changed. So I'm wondering, does the assembly still there or not?
Yes. Yeah, I think I know what you mean. So usually they assemble at neutral and alkaline pH values, the spheroidal particles a bit more than the stacked ones. I think that's just because of the geometry. At below the point of zero charge, when they are charged positively, we still see that they assemble, but not that much anymore. But we didn't really look into this a lot. So I can tell you, yes, they do, but it seems it is a bit more rare.
Okay, thanks. It's just, I'm asking this question is because for the hematite and TPM particle, I don't know if you're familiar with this one. It's reported that when the pH is like 8.5, the particle will attract the tracer particle, which is just a pure PS particle. But when they change the pH into like 6.5, it will repulse the tracer particle. So I'm wondering if it is the same case here.
Okay. I don't know exactly this work, but I will definitely look into it. Thank you.
Okay, thanks.
Sandra, there is a question in the chat box.
Okay, can you read it?
Okay, if you lay a layer phospholipid on the surface of the particles, will it affect the movement of particles and make them unable to move?
A phospholipid.
Yeah.
I have not tried this. So what would you expect happens if I put the phospholipid? I'm not really sure. So I cannot really say.
Okay, I have a question. Does the pH affect the ellipsoid particles motion?
Yes, it does. I didn't show this, but I think I have it here. Yes. Here you see the same kind of plot for the spheroidal particles, the speed and the motion mode. And you can see that the motion mode also changes when we change the pH. But for them, it's kind of the other way around. They usually move horizontal. So at neutral pH, you saw they don't do this upright motion. But if we change to pH below point of zero charge, some of them start moving upright. You can kind of see it in this video. I will show you. If you, for example, look at this particle here in the bottom right, Now it is laying flat. So now the aspect ratio makes it look spheroidal. Then when we turn on the light, it starts moving. And if you look at it now, it doesn't look spheroidal anymore. The aspect ratio changed and it is now standing up. You can see it even a little bit better in comparison to this particle here in the top. This one doesn't stand up, but this one does. So it's not such a strong effect as for the stacked particles. You can see we only observed this for around 50% of the swimmers, but we also see a change there.
Yes, thank you.
Mm-hmm.
I have a question, if that's okay.
Sure.
So basically, you mentioned, well, you scan quite a large pH range here.
Mm-hmm.
And I was wondering about, do you know anything about the stability of these metal oxide particles across these pH ranges? Would you expect some dissolution and how that would affect the motion potentially?
Yes. So I don't have this data here, but we did this kind of study. We looked, I think we only did this for the stacked particles, not the spheroidal ones. We took a fairly acidic samples, some in the intermediate regime and some alkaline ones. And then we looked at them before and after motion with SEM and XRD. And for the samples in acidic and neutral regime, they do not change. They do not change their appearance, and also the crystal structure doesn't change, so it seems they don't dissolve. But for the particles in alkaline solution, they change over time. So they dissolve. I think this is also reported for bismuth vanadate if you really illuminate them for quite a while. So usually for the motion studies, we didn't look at them by illuminating them not for longer than around a minute or half a minute. But if you do this for longer, they start dissolving. And then also, of course, the crystal structure suffers and we get other oxides and hydroxides. So then they are not that stable anymore for long.
Would you expect maybe then that some of this increased speed could be because of this ion flux, for example, that you might get as a result of this gradual dissolution? There's some papers where they mention you have these, I don't know, I can't remember if it's manganese, for example, or so swimmers in these peroxide solutions, and then they degrade, and that gives them their motion. So if you have a continuous dissolution to the extent that you're getting particle morphology changing, could you imagine that might cause some effect?
I'm sure if they really dissolve and also totally change their shape, this will of course affect the motion. But yeah, for the course of the videos we usually took, we didn't see this. Also the way of motion didn't change, so they still do this upright rotation and then they move. So I think at this point there's not a strong influence, but if they move for longer and really start changing the shape and so on, then I think yes, this will influence the motion.
Okay, thank you.
Thank you.
Sandra, there is another question in the chat box.
Okay. Okay, I will read it. In this article, it is mentioned that when the pH value is lower than 0.0 charge, the particle surface is adsorbed by positively charged hydrogen cation. Stable hydrogen bonded hydrogen peroxide clusters are formed. Why does the formation of fuel clusters prevent effective degradation? Yes, we wrote about this in the manuscript, that when the particles are charged positively, then hydrogen ions are adsorbed to their surface, and then we get these clusters. And then I think what we talked about is that then dissociated hydrogen peroxide, which needs to get to the surface to actually be degraded. So the mechanism of peroxide decomposition involves very much hydroxyl radicals. they cannot get to the surface anymore, really, because we have these clusters, and that's why this hampers the peroxide decomposition.
Okay. Any more questions from audience? If no more questions, we would like to thank Sandra again for his wonderful talk.
Thank you so much for having me.
Thank you for your wonderful talk. And the next talk will be the same time in the next week. I will see you again in the next week. Thanks for you guys attending.
Thank you. Bye-bye.
Bye-bye.